What if the future of artificial intelligence is not a bigger data center, but a smaller chip inspired by the human brain? Your brain runs on roughly 20 watts, yet it recognizes faces, learns patterns, and adapts to the world in real time. Engineers are now chasing that same kind of efficiency in silicon. The result is neuromorphic engineering, chips designed not just to calculate, but to behave a little more like nervous systems.
Traditional computers are extremely powerful, but they are built around a simple separation: memory in one place, processing in another. Data has to move back and forth constantly. The brain is different. Memory and computation are deeply mixed together in networks of neurons and synapses. Signals do not fire everywhere all the time. They fire when something matters. That difference is one reason the brain is so efficient.
In a conventional machine, information is usually stored, moved, processed, and stored again. That system works brilliantly for many tasks, but it can waste energy when a machine has to constantly sense the world. The brain does not process reality as endless full frames. It reacts through distributed networks, local connections, and bursts of activity. That is the biological clue engineers are trying to turn into hardware. Neuromorphic systems often use spikes, brief electrical events that are inspired by the way neurons communicate. Instead of pushing data everywhere all the time, they can activate only parts of the system when something changes. This is called event-driven computing. It is not a perfect copy of the brain, but it borrows one of the brain's most powerful ideas. Do less, only when it matters.
Neuromorphic engineering is the attempt to build hardware inspired by nervous systems. The goal is not to create a tiny human brain. It is to design chips that can process information in a more brain-like way: parallel, adaptive, and energy efficient. In simple terms, these chips are trying to move beyond brute force computation and toward a style of computing that is closer to perception.
This is not only a theory. IBM's True North explored a neurosynaptic chip architecture with 1 million digital neurons and 256 million synapses. Intel developed Loihi research chips and later built Hala Point, a large neuromorphic research system based on Loihi 2 processors. The Spinnaker project in the United Kingdom also explores large-scale brain-inspired computation. These systems are not human brains, but they prove the field is real. One of the clearest examples is event-based vision. A normal camera records full images again and again, even if most of the scene is unchanged. An event-based sensor works differently. It reports changes when they happen, pixel by pixel. That means less wasted data, faster reaction, and lower power. For robots, drones, and smart sensors, that can be a major advantage. This matters because the future of AI will not only live in the cloud, it will also live inside small machines that need to sense, decide, and act locally. A drone cannot always wait for a distant server. A medical sensor cannot waste power processing everything at full scale. Brain-inspired chips could help machines react faster, use less energy, and operate closer to the real world. Some of the most meaningful uses may be medical. Brain-inspired systems could help low-power hearing devices, adaptive prosthetics, and sensors that respond more naturally to the body. In brain-computer interface research, the challenge is not only reading signals, but doing it efficiently and responsively. The promise is not replacing the human mind. It is building machines that work better with the nervous system. The unsettling part is not that these chips are conscious. They are not. The unsettling part is that smaller, faster, lower power intelligence can disappear into the background of everyday life. Smarter sensors can mean better medicine and safer machines. They can also mean more surveillance, more automation, and decisions made too quickly for humans to understand. The danger is not a thinking chip. It is an invisible one.
But we have to be careful with the language. Neuromorphic chips are brain-inspired, not brain-equivalent. They do not understand the world like people do. They do not have emotions, consciousness, or human judgment. Many are still research systems, and conventional AI hardware remains more practical for many tasks. The real story is not that silicon has become alive. The real story is that computing is learning new tricks from biology.
The human brain is still the most remarkable computing system we know. Neuromorphic engineering does not prove that machines are becoming conscious. It proves something more practical, and maybe more important. Our best computers may not be the ones that only calculate faster, but the ones that learn from how nature computes. The next leap in AI may not be a bigger machine. It may be the chip that thinks.